class, welcome to the next segment in the week 4 material. And in this segment, we're going to look at one potential application of Boolean logic. And I should say just one of many potential applications of Boolean logic. Like I said, when we first started this unit, this is perhaps the most versatile and useful thing that you will learn in this class. And as you'll see during the course of the semester, you're going to be repeatedly coming back to these concepts over and over again as you're going through the course. So and in doing that, you'll sort of discover for yourself the applications for Boolean logic and just sort of building that framework. But here I'm going to talk about some more advanced applications of Boolean logic that probably required a little bit more explanation about why exactly they work. And one such application that is also something that is often very useful is something that's a little bit more geometrically oriented, so more in the realm of geometry. And that's the idea of using the Boolean logic to test if a particular point is contained within a rectangle. And you can use this for other shapes, but the math and the Boolean logic gets a little bit more complicated. The simplest examples are square or just rectangle in general. Here, this is actually going to be a square, which is technically considered a rectangle, but not something we normally think about. And it's just a square is just a special rectangle. And in the next segment, we're going to take a look at the idea of also including a circle in this particular problem. But let's go ahead and first sort of get our bearings straight so that we have a better idea of what we're actually going to be doing and what we're actually going to be proving. So in this particular program, we have two variables set aside here, an x-coordinate and a y-coordinate, that we want the computer to test and see if that particular ordered pair, that is this value of x-coordinate and y-coordinate, is in fact contained within the rectangle. And we've defined the points of our rectangle to be as follows. So the variable a here is going to define the leftmost extent of our rectangle, which is just going to be at x value of positive 10. And this b is going to define the rightmost extent of our rectangle, which is going to be at x equals positive 30. And this variable c is going to define this is actually going to be the topmost extent of our y-coordinate for our rectangle, and I'll explain why in a minute, why actually it is the topmost extent. And this variable d is actually going to be the bottommost extent for our rectangle in question here. And here this program is going to go through the process of going through a bunch of individual conditions, and again combining that with the idea of Boolean logic to test whether this particular point x, y does in fact lie within the rectangle that is given, that has these particular bounds here. So let's actually, one thing that's really helpful in a situation like this is to, of course, take a look at a graphical representation. So let's go ahead and do exactly that. So let's start off by putting up a rectangle that we're going to be working with, which again, it looks like a square. A square is just a special kind of rectangle, but you can see here the leftmost extent, again given by the variable a in our program, which is 10, and the rightmost extent given by a variable b in our program, which is 30, and then the topmost extent given by our variable c in our program, which is 10, and the bottommost extent given by the variable d in our program, which again is 30. And you might be wondering, why in the world do I have 10 plotted up here and 30 plotted down here? And the reason why is this actually, the computer's coordinate system that it uses for the screen is actually a little bit different than the coordinate system that you're used to on, say, a standard Cartesian grid in your algebra classes. So a standard Cartesian grid, as you go up, you're going towards higher values of y, and as you go down, you're going towards lower values of y. On the computer screen, that's actually reversed. As you go down the screen, you're actually going towards larger values of y. So as the mouse cursor goes down, I'm in fact going towards higher values of y. And if I go up on the screen, I'm actually going towards lower values of y. In fact, the computer's origin is in the top left-hand corner. This is considered 0, 0. And then as you go to the right, you go towards increasing values of x. And as you go down, you go towards increasing values of y. So that's why I have this drawn the way I do, just to sort of stay consistent with the computer's representation of its own coordinate system, which again, it's the same as the Cartesian coordinate system with the exception of the y-axis. And also, the origin for the computer's coordinate system is actually in the top left-hand corner as opposed to being centered on the screen. So just a couple things to keep in mind when you're working with the graphical system of the computer itself. So let's also go ahead and put our test point in here and sort of check from a visual inspection what we expect the computer to actually give us as an end result. So if we take the values of x and y that we want to test, in this case 15, 15, and we plot that on our rectangle slash square that's bounded by these points. And from visual inspection, we can see that if our program is in fact working, then it should tell us that this particular point is in fact contained within the square in question, given these values for the leftmost extent, the topmost extent, the rightmost extent, and the bottommost extent. And again, we define those variables as leftmost extent is A, rightmost extent is B, topmost extent is C, and the bottommost extent is D. So in order to accomplish this, we actually have to ask 4 different questions. And one of the first questions that we're going to have to first ask is the value of our variable x greater than or equal to A? And if you take a look at the shaded part that appears on the screen here, everything that's shaded in red, those are all the points that actually fit that condition, that fit that particular criterion. So at every point in this red shaded region, each individual point there is something that satisfies the condition of x, the x coordinate being greater than or equal to A, which in our case is just 10. So every point here, every point here is something that would satisfy that condition, x being greater or equal to A. And it may not be apparent why these particular questions are something that we're going to be asking, but when we bring it all together at the end, hopefully it will make sense why we ask these particular questions and why these specific questions. Another question that we want to ask is if our variable or our value x, our x coordinate, is less than or equal to b, again, the rightmost extent of the square slash rectangle. And again, every single point that's shaded in red here is something that is going to satisfy that condition. So if I take any ordered pair in this red shaded region, then the x value of that ordered pair is going to be something that is less than or equal to 30, something that is going to satisfy this particular condition or this particular question. So that's the x coordinate. And if we want to take a look at the 2 questions we want to ask for the y coordinate, it's sort of the same idea. So here we want to ask, again, keeping in mind the convention of the computer's coordinate system, as I go down the screen, I'm going towards higher values of y. So in this case, we want to ask if our y coordinate is greater than or equal to the topmost extent of our rectangle slash square. And again, everything that's shaded in red here corresponds to is a point that would satisfy this particular condition. So any ordered pair here, the y value of that ordered pair would give us an answer of yes to this question: is the y value of that ordered pair greater than or equal to c, the topmost extent of our rectangle? And the final question that we want to ask is if y coordinate is less than or equal to d, which again is 30 in this case. And again, the area that's shaded in red here is any ordered pair in that region, is the y value of that ordered pair is going to satisfy this condition, asking if the y value of that ordered pair is less than or equal to d, which again, d is equal to 30. And if we want to, we can actually overlay all those red shaded regions, and you can see that there's an overlap here in the center. So all 4 of those red shaded regions overlap here. And anytime something overlaps, then that's going to involve the use of the Boolean AND operator. So since all 4 of these shaded regions overlap over the square, and that's what we're chiefly interested in when we're asking if this asking where this point lies in relation to the square, since all 4 of these shaded regions that we looked at previously overlap over this square, then that means that each one of those questions that we asked, each one of those individual questions that we asked, all 4 of them, the answer to all 4 of them must in fact be yes. And it may take a while to sort of convince yourself of that, but if you consider a point that's, let me actually go back to what we had here. Consider a point that's over here. And if you think about the questions that we asked, yes, this point where the mouse cursor is, that is greater than or equal to 10, but it's not less than or equal to 30, so it can't be inside the square. And if we consider a point up here, yeah, that's less than or equal to 30, the y coordinate is, but it's not greater than or equal to 10, so that's not within the square either. And you can sort of repeat that same exercise for every single area that you see here and see that the only combination of values that can actually be in the square is something that answers yes to all four of those questions that we posed, again, with the visual representation of the red shaded regions. So in order for us to conclude that this point, again, any value of x and y that we choose, in order for that point to lie within the square, that means the answer to all four individual questions must be true. So that means this must be true, this must be true, that must be true, and that must be true. So that would then stand to reason that we would have to use the Boolean AND operator to actually accomplish in order to get the computer to actually ask that question for us and get the correct answer to that question. And if we go back to the Python program, you can see we actually have that exact same setup. So again, for any value of x and y that we choose, we're asking if that value of x is greater than or equal to a, again, the leftmost extent of our rectangle. And we also require that x be less than or equal to b, again, the rightmost extent of our rectangle / square. And we also require that y, the y-coordinate, be greater than or equal to the topmost extent of our rectangle given by the c here, which is 10. And we also require that the y-coordinate be less than or equal to the value d, the bottommost extent of our rectangle, which is given up here. And by having the AND operator involved in between every single one of those conditions, then the computer is going to require the answer to each and every one of those conditions to be yes in order for this entire if statement to be met. So if just one of these fails, if just one of these conditions fails, then the entire condition spelled out in this if statement is a failure, and it's not. And that means the computer is going to jump down to the else that appears. So this kind of goes back to the idea of the if else. When you have an if else set up, if the if statement fails, then the computer runs whatever's in the else statement. And if this statement is met, then the computer skips over what's in the else statement. And this will also sort of verify that this works. This idea of Boolean logic works in an if-else block like it would any of the if-else blocks that I looked at back in week 2. But if the answer to each one of these individual conditions here is in fact true, each and every one of them, then this entire thing in the if statement is true, and we enforce that requirement by using the AND operator. And if the answer to this entire condition in the if statement is true, then it's going to run this indentation and print out the point x comma y lies within the rectangle bounded by a, b, c, d. And if this condition fails, then it'll jump down to whatever's in the else. So if we want to get some verification of that, we can in fact run this, and you can see it does print out the point x comma y lies within the rectangle a, b, c, d. And if we want to test the reverse case of this, so here I'll make our x coordinate 5, which if we go back to our square, x coordinate of 5 would be somewhere over here, which is outside the rectangle. So that means if this program is working, then this time it should tell us our point is not within the rectangle, and you can see this time we get the result of the else statement, or the else block, printing out the point x, y lies outside the rectangle a, b, c, d. But that's going to do it for this particular segment. It's taking a look at more of a geometry-oriented application of Boolean logic. And the next segment, we're going to actually take this same example and add a circle to it. And we'll see how that process actually goes when we take a look at that segment. So that's all I have for this particular segment. So with that, I will see you all in the next segment.